So in the last class, we have discussed about the three different types of triaxial tests. So we have basically the unconsolidated undrained, consolidated undrained, and then the consolidated drained. So here in all stages, we have the undrained, I mean, cell pressure application as well as shearing. Then here we consolidate the sample, and while shearing, there is no drainage allowed, so there is development of pore water pressure. And while in the consolidated drained, in both the stages, we allow the drainage, and therefore there is no development of excess pore water pressure. Now, before going on to the shearing stage, to understand the development of pore water pressure, and what is the response of the soil, how the response of the soil actually, how the soil behaves based on the effective stress state that it has been subjected to previously. We need to understand how the pore pressure behaves in this state. So in the cell pressure application stage, how the pore water pressure develops and how it as we go on increasing the cell pressure, how the pore water pressure develops. So that is very important to understand, particularly the nature and behavior of the soil. So we in this stage we have two different points. One is the unconsolidated test and one is the consolidated state. So basically thing is that one is the undrained cell pressure application stage and one is the drained cell pressure application stage. So definitely here there will be no pore pressure development, but here there will be development of pore pressure. So we need to understand basically if we increase the cell pressure, how the soil will behave and at what point the pore water pressure actually begins to develop as per the increment of the cell pressure. All right, so we will just focus on that part first of all. So if this is clear, if this part is clear, this part will automatically be clear how the soil behaves. So yeah, before going into that, we have discussed what is the drained and undrained condition. So in the drained condition, we have a drainage open. So and in the undrained condition, there is no drainages open, so there is no volume change. So no volume change. And here there is drainage allowed. So in these two cases, when we will apply a load, this load will basically result in pore pressure development. And while here it will result in drainage from or into the sample, as we will see. All right, drainage. So basically change in volume. So these are the two different responses of two different conditions. So undrained condition and drained condition. So as we go on applying the pressure load, so here the pore pressure development will take place, and here there will be drainage. Now to understand how the pore pressure will evolve during the isotropic consolidation stage, actually it should have been how the pore pressure development will, how the pore pressure will evolve during the cell pressure application stage. All right. So as we have previously discussed, we took out a sample from a particular depth of the soil. So it is at a depth Z. So this is the soil sample. So it is at a depth Z, and there was a water table. So gamma WH is the pore water pressure. So when we took out the soil from here and we put it on the triaxial pedestal, there was no pressure acting on the soil. only the atmospheric pressure, which you can consider to be zero, or the axis we can consider it to be the axis. So we can negate the effect of the atmospheric pressure. So basically, exposed to the atmospheric pressure, it is put on the pedestal of the triaxial cell, and therefore on that sample, now at present, sigma total is equal to 0. But mind you, that sample was initially being subjected to a sigma total of, so if I write sigma I, so sigma initial, so equal to gamma into Z. Alright, so gamma we consider the unit weight of the entire bulk unit weight, alright, saturated unit weight, whatever, everything on top per unit area at this depth. So that is the total stress being acted on the soil previously before taking it out. Now when we are placing it here, the total stress on the soil is 0. So basically, if we look into the pressure present pressure, all right, so the at present pressure, and the pressure which it has been already subjected to, all right, so the total stress which it has been already subjected to, which it had already been subjected to. So we can consider this sample to be definitely over consolidated at this present state, of course, all right, at this present state. Then we have the residual water, pore water pressure here. So we have a negative effective stress at this moment. Then what we do, we start applying the cell pressure. All right, we start applying the cell pressure. So cell pressure we go on increasing. So starting from, definitely we start from 0. Then we increase to 1 kPa, 2 kPa, 3 kPa, and then we go on increasing. Now at the same time, what will happen? The pore water pressure, now drainage is not allowed at any moment. Drainage is not allowed at any moment. Therefore, there will be development of pore water pressure. Now the thing is, we have already discussed that when the soil is saturated, we have the B parameter, which is delta U by delta sigma 3, or in this case we can say delta U by delta sigma C, all right, so which is the cell pressure application. So in case of saturated soil, B is approximately equal to 1. So whatever cell pressure we increase, delta sigma C, it should result in the increase of pore water pressure in the same magnitude, in the same magnitude. But in the initial stage, it is not so. So in the initial stage, if we plot pore water pressure and the cell pressure, it should be a line inclined at 45 degree, because it should increase at same rate, all right, but it is not so, all right. The increment of pore water pressure is less than the increment of cell pressure. So the increment of pore water pressure is lesser than the increment of cell pressure. But why is that? And up to what extent this behavior of the soil will continue? So there is a limit up to which this will continue, and beyond that it will show same response. I mean, whatever delta sigma u you apply, we will get the same amount of response in the delta U, that is the pore water pressure increment. But why not in the initial stage, and what happens, what is this barrier? All right, so we will, or what is this, the point where it starts to behave as such. All right, so to understand that, so up till now, so here we see that if there is the soil element here, all right, so we consider it as to be the spring. So whenever we apply the load, if it is undrained condition, definitely whatever load we apply, delta sigma C, it should result in the pore water pressure increment, but it is not so. So to understand that, we have considered the soil to be composed of a, to be equivalent to a spring, and the pore water pressure to be the fluid in the piston. All right, so we have correlated the two, and we have seen that in the undrained condition, basically there is development of pore water pressure. All right, so this is undrained condition, and there is no consolidation occurring. And basically the effective stress state delta sigma dash is equal to 0. So sigma dash remains constant. All right, whatever it was initially subjected to, that is remaining constant. So only thing is that whenever we apply delta sigma, it results in delta U, that is the change in the pore water pressure. Whereas in the drain condition, whenever we apply a load, it will result in the drainage of the pore fluid or pore water. It will result in the drainage of the pore water, and the soil will consolidate. The soil will consolidate. So basically, the effective stress in the soil will be equal to the applied load or the applied stress. So total stress will result in increase in the effective stress. So delta U in this case will remain 0. So that is the drain condition. So we have seen, that so this is an element, right? So it is subjected to sigma 1, sigma 2, sigma 3 in 3 different directions. So these are the principal planes, and when these pressures are increased to this additional total stress, so we now have sigma 1 plus delta sigma in this direction. Similarly, we have sigma 1 sigma 2 plus delta sigma in this direction, and sigma 3 plus delta sigma in this direction. So that this is the final condition. So in that condition, what we have is, initially the pore water pressure was U. So now we have delta U. So the pore water pressure is U plus delta U. And we have seen that delta U is dependent on the increment of the confining pressure as well as the increment of the deviatoric stress. So we have two coefficients. One is the B parameter, one is the A parameter. So the A parameter is mainly related to the increase in pore water pressure, excess pore water pressure development due to the increase in the deviator load. That is the A parameter. And the B parameter is related to the increase in the pore water pressure with increase in the cell pressure. Right? Increase in the cell pressure. So we will concentrate on this part afterwards. So for this case, see, delta sigma 1 is equal to delta sigma 3, therefore this becomes 0, because here there is no delta sigma D. Alright, it is equal to 0. So whatever this stress we are increasing in this side, it is same amount is increasing on this side as well. So overall it is delta sigma 3 increment. So ultimately delta sigma 3 cancels out since delta sigma 1 is equal to delta sigma 3 during the isotropic consolidation stage or cell pressure application stage. So this cancels out and we have delta U is equal to B into delta sigma 3. So ultimately we can say delta U by delta sigma 3 is equal to B. All right. Now we have seen that compressibility of the fluid, if we say Cp, all right, that is the compressibility of the fluid, it is very, very less compared to the compressibility of the soil skeleton, all right, soil skeleton or the consolidation, this compression coefficient, all right. I mean, here the volume change with respect to change in the void ratio, with respect to the change in void ratio. So when the water drains out, when we apply load, so in that case we will have delta V, which will be given by the compression index, right? And in the undrained case, if there is a small change of volume, all right, Vp, all right, that will be governed by the compression in the pore frame. So we see that Cp is very, very less than Cc. Therefore, delta Vp, all right, is very, very less compared to delta V. So for practical cases, all right, so for practical cases, so here we see that Cp is much less than here. So ultimately this is much lesser than 1, all right, so we can say that B is approximately equal to 1. But now we have to understand that all of this discussion, up to this stage, whatever we have discussed, is basically the behavior of either loose sand or silt or normally consolidated clay. So this, whatever up till now we have discussed, we have, understood, we have visualized, is basically the response or the behavior of the loose sand or the normally consolidated clay. Now, what will happen when the soil is already being consolidated, or basically it is already being subjected to an more magnitude or more intensity of effective stress prior to the test condition? Whatever we are applying in the test, it is subjected to higher amount of effective stress at the beginning itself, all right. So here you see when we take out the sample, from the depths, so it is already being subjected to a particular effective stress which is sigma minus sigma. Then suddenly everything becomes 0, right, and there is a negative effective stress. So the effective stress and the total stress changes from this condition to this condition. So definitely this soil sample is now behaving as a over consolidated clay, or as a dense sand or silt, whatever you may consider, all right. So then we are going on applying sigma c. So we are going on applying sigma c. So we are going on 0, 1, 2, 3, 4 like this, up to the point when we come to this state. The soil will behave as definitely as over consolidated. Okay. All right. So here we see that the B parameter of such, that is why we see that the B parameter of such soil, all right, is we obtain so low values of B parameter. Right? So here we see this is a stiff soil and this is a very stiff soil. So these are actually it should have been practical values of B or realistic values of B. Right? So realistic values of B are of this sort. So we see that for soft soil and medium soil, we see that B is almost it is equal to 1. Right? Now what is basically stiff soil and very stiff soil? So here we can see that stiff soil is basically over consolidated clay. All right? And very stiff is when the over consolidation is occurring at a very high confining pressure. All right? So ultimately this soil is still now behaving as a over consolidated clay or dense sand. Now up to what level, up to what extent of cell pressure, all right, up to what extent of cell pressure will this behavior continue? So to understand that, so here we have already we have the soil, so it is subjected to the effective stress state, which is this one, all right, and then so here we see that the soil is basically compressed, all right, so it was in this state, so it has already been consolidated, all right, so in this effective stress state, all right. So then, so to understand this behavior, so what we have to first of all understand is that the soil it is not always behaving. I mean, we cannot directly correlate the behavior of the soil to the spring. All right, we cannot always directly correlate the behavior of the soil to the spring. It is not such like that. So to understand that, all right, when it behaves according to the spring and when it deviates away from that behavior, we have to understand what is the effect of consolidation or the effect of effective stress increase. All right, so here we see a loose sand and a dense sand. All right, subjected to the same amount of confining pressure. All right, so this is P dash. We will come to know what is P dash. All right, when we will learn stress path. So P, just for our case now here, P is basically the confining stress. So if I have sigma 1, sigma 2 and sigma 3 in 3 different directions, so P is basically this divided by 3. So we have P dash is equal to P minus U. Alright, so the pore water pressure is same in all directions, so as we have observed, so P minus U. And this particular effective confinement, it only causes strain, volumetric change. All right, so strain in volumetric strain. All right, it only causes volumetric strain. All right, so only causes delta V. It does not cause any shear or deviatoric or shear straining. All right, no shear. So when we apply effective confinement, all right, so we see the void ratio. This is the void ratio E. So what is the basically void ratio? It is the volume of the voids divided by the volume of the solids. So volume of voids divided by the volume of solids. So we see that with increase in the confining stress, the void ratio decreases. So the void ratio decreases, but the volume of solids is remaining intact. Of course, it will remain intact. So the volume of voids will decrease. So what will happen is that the particles will rearrange. We will see to that, all right, in the next slides. Now, when we release the load, we see that it does not go back the same path. All right, had it been the spring, all right, it would have gone in the same path from where it came, hence came. All right, but it is not like that in case of soil. So the soil is basically consolidated, and there is densification. All right, so there is densification of the soil, and that densification occurred due to the rearrangement of the soil particles. So the pore fluid went out, and the particles, they rearranged themselves into a compact state. All right, and that state now it holds. So only a small amount of elastic deformation is recovered. Only a small amount of elastic deformation is recovered. Now when we load this soil again from this state, so we will see that it will trace a path here in this manner. So here we see it was moving in this manner. Here we see it is moving in this manner. So the soil, after being consolidated to this point, it had become stiff. Then now as soon as it reached this point, it will again now come through this curve. Now it will trace the virgin curve. All right, so now again there will be consolidation. All right, again there will be reduction in the void ratio. All right, the volume of voids will reduce, and there will be drainage out of the soil, and then again the soil will again densify further. All right, further it will densify. So here we see again some small amount of deformation is recovered, but majority of the deformation has gone into the soil, and that deformation, that work is stored, that energy is stored in the soil. In the matter of, in, it is stored in the soil, correlating that to the consolidation stage of the soil. All right, so it is correlating to the consolidation stage of the soil. So ultimately, we have this soil here up to this stage. So this is a loose sand. All right, so this is a loose sand. Now, if we compact the soil, if we densify this soil to such a state that this is the void ratio here. All right, at the start of the experiment. So definitely if we load the same amount, if we load with the same amount, so here we see it is 0, 1, 2, 3, 4, 5, 6, 5 kPa, 5 MPa, then 6 MPa, 10 MPa. So ultimately we are loading the same amount. All right. So here we see instead of so much of deformation, it is showing so little deformation, so little deformation. All right, because the soil has already densified. Right. So if this densified means the soil has now become stiff. So if this spring is very stiff, if this spring is very stiff, if we apply a load, this spring will resist deformation. Right. If it resists the deformation, the pressure which is being applied, it will not be transmitted to the pore water. It is still being taken up by the spring. Alright, it is still being taken up by the spring. It is so stiff. The spring is so stiff that it does not allow even a small amount, even it does not allow CP, the compression, to take place. Alright, if it does not allow that, so the void increase in the pore water pressure will be now lower, and majority of the load which is being applied will be taken up by the soil skeleton. Right? We will see how it develops in the coming slides. Now we have to come up to a certain stage where this soil now ultimately loses its stiffness. All right, and then so we have to go on increasing the load. We have to go on increasing the load. Ultimately, we will come up to, suppose, up to this point. All right. So then what will happen? It will behave as a normally consolidated soil. So in this range, what will happen? Now it will compress the soil. All right. So the soil is now getting consolidated, and there is drainage out of the soil. All right. So this is the state here. So when this happens, of course, if we do not allow the drainage, in this case, whatever delta sigma you apply, that same amount of delta sigma will reflect in the increment of pore water pressure in this stage. All right, so not in this stage. We will see why that. So yeah, this is the behavior of sand, the behavior of sand. So the same behavior we can observe in clay also. All right, so in clay we have first of all the recompression curve, then the normally consolidated curve. All right, so we have consolidated the soil up to this state. Now from here, if it is unloaded, it will trace this path. All right, if it is unloaded, so this amount of consolidation or densification in the soil has occurred, and only this amount of deformation we have recovered. So now again when we load, it will again trace back this path, and ultimately it has to come to this point. So this is known as the pre-consolidation pressure. Right, so what happens here we will see. Right, so here the soil will trace this path. So definitely compared to the application of load, the soil, the spring is very stiff. Therefore, the pore pressure development is lesser than what it should be. It should have been. So it is delta sigma U is, I mean, suppose maybe 20 kPa. So instead of delta U being 20 kPa, we will may get 10 kPa or maybe some lesser value. All right. So that is why it is happening here. Now, what will happen beyond this, we will see. So this is for clay, and this is for sand. Same kind of behavior. All right. So ultimately, consolidation leads to the rearrangement of the particles, leads to the densification of the soil. All right, with lowering of the void ratio or a decrease in the void ratio or porosity, and ultimately what it results is that the soil it stores that particular consolidation stage. Right, that effective stress which was subjected to previously, it stores in its structure. Right, so now to understand that, we again come back. So we now see what will happen when we apply sigma c. All right, we apply the confining stress, so we see that the soil, it is getting consolidated. This is the normally consolidation stage. So from here, this is the recompression curve, and this is the over consolidated stage. Again from here it is normal consolidation stage. All right, so this is the pre-consolidation pressure for this part. Earlier it would have been subjected to somewhat like this. So this was the pre-consolidation pressure earlier. All right, so again when it is consolidated up to this point, now it is again released, again recompression, and then again here. So again we will have the pre-consolidation pressure here. So from an uncompacted state, it will move to a compacted state. Right, so this is the compression line here. So these are some test data which we have seen. So up to point here, it will trace back this one. So loading, increment of delta sigma positive. All right, then unloading. So delta sigma negative. All right, again when we load, now it will trace back this curve up to this point. From this point onwards, again it will be normally consolidated. All right, again it will be normally consolidated. So that is why we see that when the sample was loaded, all right, so we go on increasing from 0 to 1. So it is delta sigma c is equal to 1. But we see that delta u, instead of being 1, it is suppose 0.2. All right, then we increase from 1 to 2. All right, then 1 to 2 when we increase, so that is sigma c. So again delta sigma c is now 1 kPa. Now maybe delta u will be equal to 0.3. all right, in the next stage, all right. So, but the increment in cell pressure is same. So it is going on 1, 2, 3, 4, 5, 6 like that. It is going. So cell pressure, pore water pressure is also incrementing in the same. I mean, a little bit, but it will go on. The increment difference or the increment value, it will go on increasing. All right. So here we see that this soil, it was already being subjected to an effective stress of sigma minus sigma e. So here we see that with effective consolidation pressure, we see that the V value, it decreases. All right, the B value, it decreases. So how to visualize that? What happens? All right, so we will come in the next slide. So here we see that basically this soil, when we took out, so it had already one particular effective stress state. All right, then the the stress state became zero. So definitely this soil is now behaving as a over consolidated soil, all right, until it comes up to the point where then again it will behave as a normally consolidated soil. So what is that point? All right, so here we see, so this is a dense sand, so this is a dense sand here. So up to this point, this is the virgin compression curve. Similarly, this is the loose sand. All right, so loose sand will come to this point. So these are the consolidation curves. All right. So if we shear, the dense sand will, the void ratio in the dense sand will increase. All right, corresponding to a particular confining stress. All right, and then it will come up to this state. In this effective stress, it will come up to this state. In this effective stress, it will come up to this state. So this is the critical state line. All right, when we will study critical state, we will again come back to this. All right, so now we are concentrating on this portion. All right, this portion, not the deviation. So the deviation basically when we apply the deviatory load. All right. So now we know that soil is granular. So this is actual picture of a soil. All right, under an electron microscope. All right. So these are the grains of the soil. All right. So these grains you cannot see with your own eye. So you see this is only 10 micrometer. All right. So this much distance is 10 micrometer. All right. This is an actual picture of soil. So we see these are the soil particles. Then we see there are voids. There are voids. All right. So there are voids. Then there are huge voids. All right. There are huge voids. Then there are other intermediate smaller voids. All right. And then there are very small voids in between. Then there are very small voids in between. So this particular structure, we can draw a schematic of this structure in this manner. Right. So we have the particles, larger particles here. All right. Then the clay particles. All right. And they are attached to each other, and then it forms the honeycomb structure. Right. So we have the voids. We have the voids in between, and they are connected like a chain. They are connected to the silt particles as well. Right. So here, if we see here, so these are the clay particles. These are the clay particles. These are the cations. All right. These are the cations, the metal ions, and we have the silt particle. So these are the silt particles, and we have the huge macropores. All right. So these are the macropores. These are the macropores. Then we have the minor, small micropores. All right. So this is the soil structure. So we can ultimately uh, assume it to be of this manner. So from this we can say that these are connected through these points like this. It is connected So ultimately it forms a honeycomb structure. So these are the connections of the soils. These are the connections of the soils. And these are the pore spaces. These are the pore spaces. So this is the basic structure of the soil skeleton. Now, when we apply a confining stress, so what happens? So we apply confining stress P dash, all right, and this is the void ratio. So we have high void ratio here. So as soon as we, and suppose this is suppose this is 1 MPa, all right. As soon as we, or yeah, 1 MP or 0.1 MPa. This is the 0.1 MPa. Then this is 1 MPa, right, and this is 10 MPa, all right, and so on. The pressure will go on increasing. So when the pressure will go on increasing, so the soil particles, this big pores, first of all will collapse. All right, they will collapse through smaller pores. So this is one stage of consolidation. Now when I release the load again, if I release the load again from this point, it will not move back to this state because it has already collapsed. The structure has collapsed. So it has densified. The soil has densified. All right. So now the particle to particle contact is more in this soil. So it will I mean some amount of this deformation in the soil particles, elastic deformation in the soil particles, or some amount of shear deformation in the soil particles, whatever it was there. So that deformation will be recovered. So what will happen? That particles will small amount it will increase. So ultimately we will have that amount of we will recover the volume by that amount. But majority of the volume void ratio, it has already been reduced. All right. So the void ratio is reduced. All right. So volume of voids is getting reduced. So volume of solids are remaining same. All right. Water is escaping from the volume of the voids. Then again we increase. So ultimately again this pores will now collapse and it will move on to the small pores. All right, small pores. So this is again consolidated. So from here again we will, if we release the load again, we will recover some amount of deformation, but major portion of the volume of voids is lost. All right, it is not lost, actually the soil has densified. All right, so it is stored in the soil. The stiffness of the soil is now increased. All right, so ultimately we will have a very compacted state, all right, consolidated state of the soil. So if we apply load in the soil, all right, if we apply load in the soil, it will get compacted. The volume of the voids will get reduced. So how can we actually consider this particular effect? All right, so up till now we have considered only the spring. So with the spring we consider some reinforcing bars, right? Some reinforcing bars here. So if I consider the strength of this reinforcing bar of this reinforcement, to be equal to the pre-consolidation pressure. So what will happen? Now we take out the sample from the depth, so it has already been pre-consolidated. So we have a pre-consolidation pressure. Suppose it is 100 kPa. So it is 100 kPa. So this is the pre-consolidation pressure. Now suddenly we put it in the triaxial cell. Now as soon as we put it in the triaxial cell, the total stress on the sample is 0. So it is somewhere here. Alright, somewhere here. Now thing is that it is already consolidated to this stage. Alright. So this is 0. So we have the void ratio, suppose at this state. So what will happen when we will keep on loading the soil now, keep on loading the soil, until and unless it reaches this effective stress state, the soil structure will be very stiff, right? And most of the load will be basically taken by the reinforcement here. All right, so the reinforcement will not allow any sort of consolidation in the soil. Now, as soon as the pressure is increasing, all right, so some amount of very small amount of compression will be there. So the curve will move in this direction, all right? If it will move in this direction, in this way. As soon as it reaches the pre-consolidation pressure, so this reinforcement, since it is the strength of the reinforcement is equal to the pre-consolidation pressure, so this will break. We assume, all right, we assume that this will break. So as soon as this will break, what will happen? Now the soil will behave as normally consolidated soil. So now whatever load you apply, it will cause either change in pore water pressure, all right, directly whatever delta sigma you apply, it will result in the same amount of increase in the pore water pressure, or if drainage is allowed, then it will result in normal consolidation of the soil. Then it will result in normal consolidation of the soil. All right. So the soil was in this state. All right. So it is in this state when we took it out of the sample of the ground of the ground. We took it out, and it was in this state. So it had a structure. So as soon as it reached the pre-consolidation pressure, all right. So it was already subjected to a effective stress. So total stress, whatever it was, so total stress minus the pore water pressure, so effective stress equal to total stress minus pore water pressure was equal to 100 kPa. So that is what it was subjected to in the in situ condition. So it has already formed an equilibrium structure to that effective stress. So this is the equilibrium structure. Suppose, all right, suppose we say. Now as soon as we reach the pre-consolidation pressure, this structure will start rearranging itself. All right, it will break. All right, so it is no longer under equilibrium state, so it will break. All right, but not, it will not totally collapse. All right, you do not think of it as a card house where you just give some displacement and the entire card house will collapse. It is not like that. All right, so the bigger force now will consolidate. All right, and there will be change in the void ratio. So this should have been 7, I think 6 5. This should have been 6 5. This is 6 and this is 5 5. Okay, and this is 7 and this is 7 5. So anyway, those can be corrected. So what the thing is that as soon as we reach the pre-consolidation pressure, just like here we have the fracture of this reinforcement or breakage of this reinforcement, similarly we have the structure reorienting itself. All right, so it will now reorient itself to a denser state. It will reorient itself to a denser state. All right, so this is the consolidation happening. All right, now if again we revert back, all right, if we revert back, if the spring, if the soil had behaved like a spring, it would have been in this manner. right? It would have been in this manner, but it is not a spring, it is a soil, and therefore the densification which it had received, the consolidation which has undergone, that will be stored in the soil, and therefore it will revert back through this path. Right? Now again, if we load, the compression will be like this up till it reaches this point. Right? So now there will be a new set of reinforcement in the soil. So now there will be a new set of reinforcement in the soil which has a higher pre-consolidation pressure. So as soon as it reaches this, again it will start behaving as a normally consolidated soil, and it will trace through this curve. All right. Here, so here if we consider this state, so here we have sigma dash is equal to sigma minus u. So this is sigma total stress, and this is u for water pressure. This is u. So it is equal to 100 kPa. So unless and until this sigma c reaches a value of 100 kPa, the soil will behave as a over consolidated soil. So it will be somewhere like this. Right? As soon as it reaches 100 kPa, now it is a normally consolidated soil. So now, if we allow drainage, definitely the soil will get consolidated. If we do not allow drainage, whatever increment in delta sigma c we apply, same amount of increment we will observe in the pore water pressure. All right, but not exactly same. I mean, mostly same. All right, mostly same. So this is the isotropic consolidation curve. All right, so we have one particular confinement correlating to the void ratio. We have the critical state line. We will know see what is actually the critical state line. All right, and this is the virgin compression, and we have the K naught consolidation, the odometer test that we do, the consolidation test that we do. So in that consolidation test, what we do is we do not allow any horizontal deformation in the soil. Only thing is we allow vertical compression. So that line will actually lie somewhere between these two. Right? So this is in the triaxial cell. So when we apply sigma c, so sigma c when it is p dash is sigma c. So this void ratio, this is the correlation. If we do the K naught consolidation, all right, so in the consolidation test apparatus, if we do, we will get somewhere in between the curve, all right. So this is P dash again, compared to that, the void ratio, all right. So in the consolidation apparatus, we generally get a lower void ratio compared to the triaxial cell. Why it is that? Because it is a K naught. So sigma V is basically higher than sigma H. So we have a shear component also. So what happens due to the shearing of the sample, some amount of shearing, not total. So there is quicker rearrangement, all right. So there is quicker rearrangement, quicker settlement, or more amount of settlement in the soil. So lesser amount of void ratio, all right, corresponding to the same this pressure. And while we shear the sample, when we apply the deviatory stress, we get this critical state line. We will see what is the critical state line. All right. So basically, in the second stage, until and unless we come up to the stage of the pre-consolidation pressure of the actual in situ state. All right. So sigma dash in situ, until and unless this is, so sigma c is equal to that, all right, or basically actually sigma c dash is equal to that. Up to that point, the soil will behave as a OC soil. When it breaks that barrier, all right, so it will be NC. So that is why we observe lesser B value in stiff soils, all right. So in stiff and very stiff soils. So stiff and very stiff are basically relative terms, all right. So they are all relative. Everything is relative, right? So void ratio, confining stress, then the B parameter, all of these are all relative. All right, so we will see when we draw the stress path and all those things. So I hope you have understood what is the mechanism. So once the soil now moves on to the normally consolidated state, so we have a normally consolidation curve. So where as the effective stress goes on increasing, we have a decrease in the volume of the soil, or if it is drained state. If it is undrained, definitely that drainage is not allowed, and therefore it will result in change in the pore water pressure or the increment in the pore water pressure. So we have seen that the stiffness of the soil also affects the change in the pore water pressure. But that is not the entire thing. So if the soil is partially saturated, so B parameter, if we have less than 1, simply does not mean that the soil is over consolidated. All right, the soil is over consolidated. If the soil is partially saturated, so what we have, this is air, all right, and this is water. So compressibility of water is very high, but compressibility of the air is very low. All right. Sorry, compressibility of air is very high. All right, so very high. That is, for small amount of load, there will be high amount of compression in the air. But compressibility of the water is very low, so it is almost incompressible. So what will happen if it is partially saturated? The voids which are filled with air, those voids they will compress. So if there is compression, that means some amount of total stress will be taken up by the soil skeleton, and the effective stress in the soil will also change. All right, so in that case, whatever increment of total stress we give will not be equal to the increment in the pore water pressure. So that is why we see here, experimentally people have determined that. So if the soil is saturated, all right, so if it is saturated, this is saturated state, so degree of saturation is 100% here. So we see that whatever load is applied, all right, of course for normally consolidated, all right, or normally consolidated soil, all right. So this is again for normally consolidated. Whatever load is applied, the same amount of load is actually being taken up by the pore water pressure. So we have the B parameter almost equal to 1. All right. So it goes on increasing in this manner. And as the degree of saturation is decreasing, so that means we have volume of voids filled with air. All right. Air is compressible. So, all right. So some amount of compression in the soil skeleton occurs, and therefore delta U is, the pore water pressure is not as it should have been as in the case of saturated soil. So we have a decrease in the B parameter. All right. So it is not always the case of only over consolidated soil. If it is partially saturated soil also, the B parameter may be less than 1, as we have seen here. All right. So up till now we have discussed about the B parameter. All right, so it is already time up. So we have seen that the B parameter is dependent on various factors. All right, so the over consolidation, or the pre-consolidation stress, then the saturation of the soil. All right, and when it will behave as a over consolidated soil, and when it will start behaving as a normally consolidated soil. All right, so what is basically the relevance to the effective stress state? All right, So in the next class, we will discuss about the A parameter. So before that, we are going to discuss one very important point of soil, that is the critical void ratio. What is the critical void ratio? As we have discussed here in this slide, if you see, we have already discussed what is the critical void ratio. So this is a critical state line. So this is a critical void ratio line basically. All right. So here also we have discussed. So when we shear at a particular confining stress, the void ratio moves to a particular value. All right. So it moves to a particular value. So that is the critical void ratio. We will discuss that in detail in the next class. All right. So this is next class.